Hello and welcome back to another past paper walkthrough. This is paper 1 from October-November 2023, and this is for Cambridge IGCSE and O-Level Computer Science. Just to recap, paper 1 and paper 2 both are an hour and 45 minutes. They both are weighted at 50%, and they both have a total marks of 75. Okay, maximum marks 75. Paper 1 is based on topics 1 to 6 of the syllabus, and paper 2 based on topics 7 to 10. And remember, just one final note, no calculators are permitted for either paper. Okay? So here we go. Here's the paper. Remember to write in blue or black pen. This is what you'll get, or something similar, on exam day. Okay? Go through the grade boundaries for this particular paper, or these particular papers. This was from October, November 2023. I'm looking at, for this particular paper, component 1.1, as you can see here. The maximum marks were 75, as I mentioned. What we would do, you would combine component 1 with component 2 down here. 1.1 and 2.1, paper 1, paper 2. And as you can see, if you were getting over 103 marks out of 150, you'd be looking at an A star. So realistically, you only need about 69-70% in order to get an A star on this paper. Okay? So it is, just to warn you, it is quite a tough paper in parts. So let's get started. Starting with question 1. A student uses a computer and several hardware devices to complete his schoolwork. The computer is a central processing unit, CPU. The student uses a keyboard to complete his schoolwork. Tick one box to show which type of device the keyboard is. Well, it's obviously an input. It's not a memory output or storage device. It is an input. The student uses a printer to print the schoolwork. Okay, and a printer is obviously an output device. The component in the CPU sends signals to manage the fetch, decode, execute cycle. State the name of this component. It is what they call the control unit. Okay, is a device that manages the fetch, decode, and execute cycle. The CPU has a clock speed of 2.4 gigahertz. Describe what is meant by 2.4 gigahertz clock speed. 2.4 gigahertz, that would be 2 billion, or rather 2.4 billion, yeah, 2.4 billion cycles per second, okay? 2.4 billion cycles per second, because we've got gigahertz. So 1,000 equals 1 kilobyte. 1,000 times 1,000 equals 1 megabyte, and 1 million times 1,000 equals 1 gigabyte. Okay, so kilobyte, megabyte, gigabyte, times in by 1,000 each time. So 2.4 billion cycles per second. The CPU contains registers including the MDR, the memory data register. Describe the role of the MDR in the fetch, decode, execute cycle. The MDR, what does it do? A memory data register. Well, first of all, I would bullet point this because it stores data. Okay, that would give me 1 mark. It stores data. What kind of data does it store? It stores data which has been fetched, yeah, referring to here, stored data which has been fetched and ready to be written into memory. So it stores data, data which has been fetched and ready to be written into memory. Okay. Identify 3 other registers contained in the CPU. Okay, well, there's the MAR, we've got the MDR, we've got the MAR, which is the memory address register. Okay, we've got the PC, which would be the program counter. We've got the accumulator, and we've got the CIR, which stands for the current instruction register. Okay, as part of your revision, it would be worth drawing out a von Neumann diagram with all the registers, the buses, so you have a clearer understanding, because these questions will come up. Okay, so that's all of question 1. A car park has a payment machine that allows a customer to pay for their parking. The cost of parking is displayed as a denary number, okay, a base 10 number, on the screen of the payment machine. The cost of parking is stored in 2 8-bit binary registers. For the parking cost of $10.50, register 1 stores a denary value of 10. Register 2 stores a denary value 50 as binary. give the parking cost that could be displayed on the parking meter when the register stores this and this. Okay, so we've got two registers. The register 2 is obviously 50, register 1 is 10. So let's have a little look and draw this out. 1, 2, 4, 8, 16, 32, 64, 128 would give us our 8-bit register. I'm just going to change the color. Okay, so register 1 has got a 1, no 2s, no 4s, no 8s, but it's got a 16. Okay, 0, 0, 0, so that equals 17. Whereas register 2 has got it's got 64, no, 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 yes, yes. So it's got 64, a 4, and a 2, which adds up to 70. 64 plus 4 plus 2, 70. So the number we'll be looking at is $17.70. Question part B. A parking cost of $14.98 is displayed on the parking machine. Give the 8-bit binary number that is stored in the register to display the parking cost for register 1 and register 2. So I'm just going to come back up here like this so we can see, and we've got 14. Okay, 14. So let me just, so we've got 14, we've got 98. So I'm going to do 14 first of all. So 14 would be one lot of 8. 4 would give me 12, a 2 would give me 14, a 0. That would be 14, so I can put zeros in these. So 8 plus 4 plus 2 equals 14. Okay, so that register would be 0, 0, 0, 0, 1, 1, 1, 0. Okay, now for 98, 98 here, we've got a 60, we've got 0. 128 doesn't go into 98. 64 does go into 98. So minus 64 equals 4 and 3. So we've got 34 left. So that means we've got 32, but then we've only got minus 32, which means we've got 2 left. So that would be 0, 0, 0, 1, 0. So we've got 64 plus 32 equals 96, plus 2 equals 98. So register 2 would be 0, 1, 1, 0, 0, 0, 1, 0. Okay, and that would give us our answer there. Oh, I've got working space there. I didn't need it. I used the working space from above. C above. Okay. The payment machine gives the customer a ticket when they have paid their parking cost. Each ticket is a 4-digit hexadecimal ticket stored as binary. The binary number is this. It's stored customer ticket. Give the hexadecimal ticket number that would be displayed on the customer's ticket. So we've got to convert this number into hexadecimal. So if I write this out, 1, 3, 4, 5, 6, 7, 1, 1, 1, 1, 0, 1. Okay, and I'm going to break this down into nibbles. So 1, 2, 3, 4. Okay, so I've got 4 nibbles here. So I'm going to go 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. Okay, so 8 plus 4 in this first number, 8 plus 4 is 12, plus 1, this would be 13. Let's leave that for now. That would be 3, that would be 0, and this would be 10. Okay, so in hexadecimal, when we get up to 10, 10 equals A, 11 equals B, 12 C, 13 D, 14 E, and 15 equals F. So here we've got 13, so this would be D. This is obviously remains the same 3, that remains the same 0, and then here we've got 10, which would be A. So the correct answer is A03D. Okay, so the number we're looking for here is A03D. Explain why data input into the payment machine needs to be converted into binary. It's an embedded system using binary computer language, E.G, ones and zeros. Okay, ones and zeros act as switches, logic gates. The switches either on or off. So like a washing machine, it's basically an embedded system. An embedded system with a CPU in it is going to use a language binary. E, oh my word, for 4 marks. When a customer is leaving the car park, they arrive at the barrier. The customer needs to insert their ticket into the system or at the barrier. The system reads the ticket number, then checks whether the parking cost has been paid for the car. The barrier is raised if it has been paid. The system uses a microprocessor. Of course it does. Okay, an embedded system. Describe the role of the microprocessor in the system and how it checks whether the parking cost has been paid. Well, let's do this as a sort of a step-by-step instruction. So first of all, what is it doing? It's compare ticket number, compare the ticket number with stored data. Okay, system reads the ticket number and checks whether the parking cost has been paid or not. Compare ticket number with stored data stored in the memory as a database. So we've got a database full of numbers. Check if ticket has been paid, usually a Boolean flag. Check if ticket has been paid, usually a Boolean flag, yes or no. If ticket equals paid, raise barrier. Send signal to. Okay, if ticket equals paid, raise barrier, send signal to actuator motor to raise the barrier. If ticket equals not paid, barrier stays down. Okay, so simple selection there, if else. So it compares the ticket number with stored data, which is stored in the memory as data on the database, checks if the ticket has been paid, usually a Boolean flag has been created. If the ticket is paid, raise the barrier, send a signal to the actuator. If the ticket is not paid, the barrier stays down. Okay, question 3. The table contains 4 descriptions about a computer system. Complete the table by writing the correct term for each description. It collects them. We've not got any terms, not been given any terms, I don't think. No, we haven't. A collective term for the physical components of a computer system. Okay, well, the physical components equals the hardware. Now, with that in mind, I'm assuming there's going to be software somewhere. So, here we go. Okay, a type of software that provides services that the user requires and allows the user to perform tasks on the computer. Okay, so any software that's been installed, really, Adobe Photoshop, or things online software such as Google Sheets or Google Docs. So it would be sort of application-based software. So application, a type of software that manages the main functions of the computer, including managing files and managing memory. This would be the OS, the operating system. Okay, a type of software that is stored in the read-only memory ROM. It includes the basic input-output system BIOS, okay, and the bootloader. Now, this one is a tricky one you might not know, but it's called firmware. Okay, basically, firmware usually comes from the operator. So if you've got a computer, a MacBook, or you've got a Dell or an IBM computer, the firmware is from that particular firm, and it's a software that is needed to sort of boot up the computer, known as firmware. Okay, question 4. Data is transmitted between a computer and a printer. The data is transmitted 1 bit at a time down a single wire. The computer can transmit data to the printer, and the printer can transmit data to the computer using the same connection. Okay, circle the 2 data transmission methods that can be that will transmit data in this way. Okay, well, simplex, no. Okay, because simplex is only in one direction. And then we've got full duplex, we've got half duplex and half duplex. So circle the 2 data transmission methods that will transmit the data. So what have we got left? Circle the 2 data transmission methods that will transmit data in the way. Parallel full duplex, serial full duplex, parallel half duplex, serial half duplex. The data is transmitted 1 bit at a time. 1 bit at a time. So it must be serial. Okay. So it's going to be one of those 2. It's transmitting in both directions. It doesn't mention that the one has got to wait for the other one. It can transmit data backwards and forwards. So it is going to be serial full duplex, and it's going to be serial half duplex. Okay. Part B for 4 marks. An odd parity check is used to detect errors in the data transmission. Explain how the odd parity check detects errors. So first of all, if we're using parity bits, so let's say we've got 7 bits of information, 1, 2, 3, 4, 5, 6, 7. This number here would be the parity bit, okay, at the end. So, example, okay. So there we go. So what it's going to do, it's going to count the number of ones are counted in the byte information, okay. The parity bit is added to ensure each byte has a odd value total. So there's my example. So this would equal 3 times ones, okay, which would equal odd, okay. E.G 100100001 equals odd. Yep. If even number is counted, an error is detected. Okay. If even number is counted, an error is detected. So that would get us a 4 marks, I would have thought. So I've got to put my example in. Always good to have an example. Yeah, put the example in there. The parity bit is added to ensure each byte has an odd value number, value total. Okay, for 1 mark. Another error detection method sends the data from the computer to the printer. Then a copy of the data received is sent back from the printer to the computer. The 2-step sets of data are compared to see if they match. State the name of this type of error detection method. Basically, when it bounces information back to see if it matches, this is called echo. Okay, bouncing back, an echo check. Question 5. A musician is recording herself playing the music for a song on the piano. Explain how the analog sound is recorded and converted to digital. I think the easiest way of doing this is to draw a diagram. So I'm going to draw a line across here. I've created a basic sound wave, and we're talking about analog sound, recording it and turning it into digital. Okay, I want to talk about, first of all, sample rates. So sample rates are basically the lines, samples in between each wave. And the more lines, the more samples we take, the better the quality of music. So we've got maybe quite a low sample rate here, okay? But what we've also got is something called the amplitude. Now the amplitude is the height of the wave. And do this very, very tight. Okay, so got 2 examples here. Now each of these, where it hits the line, is where we would take a sample. And here, obviously, it would be a lot more complex. Okay, so where these lines cross on the line, that's where we would take our samples from. For a standard, we'd be looking at something like 16-bit and 48 kilohertz. I think this is sort of standard sort of CD, DVD sound. Okay, obviously we can go up 32 bits, 64 bits, 32 bits, okay, and we'll do 192 kilohertz. Okay, so it's a very complicated sound. Basically, we've turned analog, which is a smooth curve, into sort of steps, obviously really, really tiny steps. So that's how it works. So to try and explain this, sound needs recording using an input device, microphone. That's number 1. And then the sound wave is sampled, okay? Sampled to get the amplitude, okay? What's it worth? This 5 marks. So the sound is recording in a microphone. The sound wave is sampled to get the amplitude. Each of these binary value. So each amplitude value, okay? Each amplitude value is a unique binary value. Now we can set the sample rate, number of samples per second. Okay, this is this. And then I'm just going to go up here. A bit complicated this. When we have both amplitude and sample rate, we can set the sound resolution. Okay, E.G number of bits, E.G number of bits, sample converted to binary. Okay, oh my word. So that is it. I hate the silent. I must be honest with you. I really do not like the silent questions. It's the ones where the students sort of struggle. Basically, you're turning a curve, yeah, into steps in order for the computer to be able to read it. So that's basically it. So a curve into steps would give us digital, analog to digital. I hope that explains it. It's not the greatest answer, but I would hope the examiner could understand that and get 5 marks. Okay. State 2 ways that the accuracy of the recording could be increased. Well, this is easy. I'm just going to go back to a normal color. And we've mentioned it there. Increase the sample rate, increase the sample. And then the final part for 3 marks. The musician compresses the sound file using lossless compression instead of lossy compression. Explain why the musician would choose to use lossless compression instead of lossy. Good question. I don't know why I want to do that. Generally, we would always use lossy on sound, but he doesn't want to lose any quality. He wants to make sure it's exactly the same as the original. Therefore, he would choose not to get rid of anything. Lossy compression, it gets rid of the range which not necessarily a human can hear. So we'll put some bullet points in. Keep as close to original recording as possible. Okay, that's the main reason why you would do it. By using lossy, this would reduce the sound quality. Okay, so it's basically it's the same thing, but in reverse. So it would get you 2 marks. Also, using lossy would permanent remove data, whereas lossless, no data is lost. Okay, so that would give us 3 marks. It's basically the same thing written 3 different ways. Okay, but remember, bullet point your answers, and if it's worth 3 marks, give 3 bullet points. Okay. D, the musician. We're still talking about the musician. The musician types the words for a song into a document. Okay, so we're not doing sound anymore. 2 character sets can be used when converting text to digital. And these are American Standard Code for Information Exchange, ASCII, and Unicode. Explain the difference between ASCII character sets and Unicode character sets. There are more characters in the Unicode character set. More characters in Unicode. Okay, that's worth 1 mark, I would have thought. More characters in Unicode. So we need 4 marks. What else can we think of? ASCII supports, with this in mind, because there's fewer characters, supports fewer languages. Okay, ASCII has 128 characters, each represented by a 7-bit number. Unicode is 16 or 32-bit. Yeah, so as you can see, there are a lot more characters. Unicode supports emojis. Yeah. Anything else? I think that's it. Unicode supports emojis. ASCII is 128 characters. Some text, there is a thing called extended ASCII, which gives you 256 characters. But generally, normal ASCII, it's not say it doesn't mention extended ASCII. ASCII supports obviously fewer languages. More characters are available with Unicode. Certainly at 32-bit, we're looking at 4.3 billion. 4.3 billion. Okay, so yeah, so that would be it. Draw an annotated diagram to demonstrate how a firewall works. And this is 4 marks. Okay, obviously I need a computer, so with my keyboard, and I've got either, let's put internet or a network. Okay, so how it works, basically, the firewall is a barrier, yeah, between them. Okay, this is my firewall. So when the computer sends a request to the internet or the network, it's got to pass through the firewall, okay, and then coming back again, it's got to go through the firewall. So how does this work? But traffic passes both ways. So let me write some notes. Traffic passes through firewall in both directions. Okay. Firewall has a set of rules, criteria, protocols, which data from network or internet must follow. Traffic is compared to criteria. Traffic is accepted or rejected based on criteria. E.g., games may not be allowed, and therefore, when requested, the firewall will block, usually based on blocking certain websites. Okay, so at school you might have a network whereby you type in certain things and you'll see that a message comes up saying this site has been blocked. That is the firewall. Now in our school we use something called smooth wall, which blocks a particular website. The firewall is basically monitoring the traffic, monitoring the request to and from the internet. Okay, so that is what I would use there. Let's try and zoom out a little bit on that. Okay, question 7. Complete the statement about data packets and packet switching. We've just done this in A-level. Use the terms for the list. Some of the terms in the list will not, remember, be used. You should only use a term once. And it's for 4 marks. There's 4 terms going to be used. Data is broken down into packets. A data packet as a packet, okay, destination, address. Well, yeah, okay, it does have that. It has header, footer. No, it has a header. Last, main data packets. It has a payload. Router, server, trailer. Okay, so it could be one of those that contains the packet number and the. So okay, so the header in a packet, yeah, has the packet number and the. What else it usually has a destination address as well. Okay, address where the packet's going. Okay, so that one's done. Each packet could take a different path set from the sender to the receiver. This is controlled by, it's generally controlled by routers, okay, or something called nodes. Packets may arrive out of order. Once the something packet has arrived, the packets are reordered. I assume it's the last packet. Okay, once the last packet has arrived, yeah, they're put back in order. So that would give us 4 marks. Nice and easy. Question 8. Storage can be described as being magnetic, solid state, or optical. Give 2 features of magnetic storage. Outdated. Uses a disk platter, like a plate that spins. Okay. It uses a magnet, or in this case a magnetic field, to read the binary values on the platter. Okay. It's non-volatile. It doesn't remove the data once the machine has been turned off. I mean, you could just put it uses magnets. Non-volatile uses magnets. Give 3 features of solid state. Okay, no moving parts. Okay, unlike the disk that spins on the magnetic, this has got no moving parts. Instead, it uses transistors, switches, ones, and zeros. Okay, uses, and this is where uses logic gates or control gates. And just finally, it's non-volatile, but can be volatile. Yeah, so that would be that. That's question 8. And 8C, just to finish off this question, give 1 example of each type of storage. Magnetic would be an hard disk drive. Solid state would be SSD. Okay. Optical would be a CD. Okay. I can add some more. Let's have a look. Magnetic. Back in the day, you may remember floppy disk. Again, this magnetic is old technology. Solid state, USB flash drive would be a good one. SD card, the camera. Okay, and a CD or a DVD or a Blu-ray, yeah, disc. And that would be it. Question 9, the final question. An interrupt is a type of signal that is used in a computer. State the name of the type of software that manages interrupts. Okay, in the past, I cannot remember when an interrupt question came up, but we've got quite a big one here. It's worth 1, 6, 7, 8, 10 marks. 10 marks at the end of question 1, so we need to get this right. So an interrupt is a type of signal that is used by a computer. Okay, well, what is an interrupt? Well, imagine you're playing a game on your computer and you suddenly press a key on your keyboard. When you press the key, it's like sending a message to your computer saying, hey, I need your attention now. So your computer receives the message, which we will call an interrupt. Not all interrupts are the same. Some are more urgent than others. For example, if you press the power button on your computer, that's a super urgent interrupt because your computer needs to respond quickly to shut down properly. So when your computer gets an interrupt, it checks how urgent it is. It's like sorting mail. Urgent letters go to the top of the pile, and the computer decides which interrupt to handle first based on its priority. Okay? Once the computer knows which interrupt to deal with first, it sends that interrupt to the CPU. The CPU then stops whatever it is doing at that moment and pays attention to the interrupt. Okay? So basically, that's an interrupt is basically stopping something and sending a message to the CPU to see how it should be dealt with. The type of software, well, that's going to be the operating system. Okay. You may also have heard of interrupt handler. Okay. Part of the operating system. Describe, this is for 5 marks, so we need some bullet lists again. Describe how interrupts are used when a key is pressed on the keyboard. Well, I've just sort of glossed over it quickly. 1. Key press generates an interrupt. Okay. 2. Handler determines importance of interrupt. Okay. 3. Then the interrupt is sent, as we mentioned, to the CPU. Okay. What happens next? It's placed. It is placed in a sorting queue. In a sorting queue, the CPU stops its current task and deals with interrupt. I think that would get the full marks. But here, priority interrupts such as power off are dealt with first. Okay, I think that will do. That will get us the 5 marks. Okay, now for 2 marks, interrupts can be hardware-based or software-based. A key press is one example of a hardware interrupt. Give 2 other examples of a hardware interrupt. It's basically anytime something happens. A good example is a printer. Printer sends interrupt if there is problem, E.G, out of paper or paper jam. Yeah, I'm trying to think what else has got something similar to a keyboard. You could argue the trackpad on your laptop, or even a mouse. Okay, so similar to a keyboard, mouse, when button is pressed, this sends interrupt. Okay, so I'm clicking. Might want to open a document, close a document. So this will be fairly quick for the CPU to process. Okay, give 2 examples of software interrupts. Software, we could put, and I'll explain this, division by 0. Imagine you're trying to share some sweets equally among your friends, but you don't have any sweets. You try to divide them equally, but you can't because you have nothing to divide. So similarly in computer programming, if you try to divide a number by 0, it's like trying to share something when you have nothing. This is a problem because dividing by 0 doesn't make sense in maths. Doesn't make mathematical sense. Okay? When the computer encounters this situation, it raises an interrupt to say, hey, something's wrong here. You can't divide by 0. Okay, so that's one example. Also, we've got something called null value. Okay, again, you're trying to find your favorite book on the bookshelf, but someone tells you it's not there. So you search and you search, but you can't find it because it's not on the bookshelf. In computer programs, sometimes we look at for information that isn't there, just like searching for your book that isn't on the shelf. This information, this missing information, is often represented as a null value. When a program tries to do something with null data, like trying to use a book that isn't on the shelf, it doesn't work. This triggers an interrupt to say, whoa, wait a minute, you can't use something that doesn't exist. Cannot access a file data which doesn't exist. Okay, so there's a couple, null value and division by zero. I don't know where that is in the book, but hey ho. So thank you very much indeed for watching. Good luck with your exams, and I will see you for paper 2 very, very shortly. Thank you very much indeed. Bye for now. Please continue to ask questions, leave your comments, hit notifications, and please subscribe. And finally, if you wish to buy me a coffee, I'd be truly grateful. Please visit buymeacoffee.com/learning zone. Thank you very much indeed. See you next time. Bye for now.